So let's look at these forces. From now on, up until we get to friction, we introduce a new force. Every time you have an object, you have a particle, you have something to look at, you look for these four forces and make sure that you take into account these four forces. So important forces. Right? What are these forces? Let's just start with the one that we know. Weight. We introduce weight, right? Play around with color a little bit. There you go. Weight. When we talk about law of gravitation, we actually use that law of gravitation to find the equation for weight, right? We said W, or weight, is equal to mg. Basically, it's a force due to the gravity applied to that object from the Earth, and mass would be the m would be the mass of the object, right? M the mass of the object, g is the gravitation due to acceleration due to gravity. Second force, one force that you have to take. Second force is called the smooth contact, but you might also know it as normal force. Right? I'll put it there. Smooth contact. Parentheses, normal force. Now this smooth contact or normal force is tightly, kind of loosely related to Newton's third law, right? Action and reaction law, if you remember. Meaning that when for any action there is a reaction in opposite direction, same magnitude, right? Collinear. And we're talking about Newton's third law. So following that, when we have an object is resting on a smooth surface, there's a reason we call it smooth contact or smooth surface, because later on we introduced friction in this course, and you will see that the surface cannot be smooth, doesn't have to be smooth, right? Then you're going to have an extra force. So I said up until now, you just think about these four forces I introduced today. There we'll add friction to this collection. So if we have an object, a particle that is resting on a smooth surface, then that surface will exert a force on the object that is normal to the surface at the point of contact. So again, you have two objects in contact with each other. The good example of it, something sitting on, let's say your computer sitting on a desk, or remember I was talking about the glass, this mug sitting on my hand. Well, gravity is pulling it down, weight, the first force I introduced. Right? Now, why is it not falling? Because of a smooth contact or normal force. The reaction from my hand to this mug, it's canceling the effect of weight, and that's why it stays in equilibrium. Summation of forces are zero, it's not moving. To have a motion, the summation of forces should should not be zero, should be something in a specific direction. That would go into Newton's second law, right? So let's say we have a surface like this. Intentionally I'm going to draw it in an angle instead of a straight, and let's say we have an object sitting on it. I'll take it as a wheel, something circular. Now, going to forces, we have a gravity or weight is always downward. Let's use a different color for forces. This is the force downward. Gravity or weight is always downward. So that's W. Now, at the point of contact between this object, could be a wheel, could be some barrel, and the surface, the black line I draw there, the surface is exerting a force on the object that is normal to that surface at the point of contact. So if this is the point of contact, This would be the force. Pay attention, this becomes very usually represented with N, normal force. You always look at the point of contact and look at the surface that the object is in contact with. In this case, this spherical object or cylindrical object. In contact with this surface, the force you put as normal force should be perpendicular or normal to that surface applied at the object exactly at the point of contact. So I'll put it here. If an object rests on a smooth surface or is in contact with another smooth surfaced object, right? The surface, that surface, smooth surface, exerts a force on the object that is normal to the surface. The surface at the point of contact. So you need to know two things. Where is the point of contact? And you need to know the surface so you can put your force or normal force or smooth contact force perpendicular to that surface. These two, another two. So this third one, which is we haven't talked about before, is the force due to a spring. So the third one, called spring force. Or I'll just simply put springs. Now, when you have a spring, I have a spring there. It's a tension spring, so I can only stretch it. I can't compress it, but strings can be compressed and stretched, depending on what kind of string I have. If I have a string, if I stretch it, in this case, I can only stretch this. The magnitude of the force exerted on this spring, because I'm stretching it, is related to the amount that I stretch this spring from its initial length. So if this is the initial length, I stretch it, the force exerted on this spring, and as a result, the spring exerted on my hand, Newton's third law, action and reaction, same force, is proportional to the amount this string is stretched. Now, it can be elongated in this case. I'm elongating this spring. It can be compressed. I can't compress this spring. It's not a type of compressed spring that you can compress. But it also can be kind of spring and compress. A good example of it is the springs you see in your cars, like as shockers. So the magnitude of the force due to force, let's put it this way, exerted on a linear spring. The reason I put linear here, you don't need to be worried about nonlinear spring. A linear spring is proportional to the spring elongation or compression. If we show that with the, let's go with this, force in the spring with Fs is proportional to, just is proportional to S, the amount of elongation or compression. So if you measure the amount of force, and the amount the spring is stretched and plot that on a graph like this, let's say you're measuring how much force you're applying. You can measure like 5 newtons, 10 newtons, 40 newtons, 50 newtons, and measuring how much the spring is stretched, S. Right? 1 inch, 2 inch, 3 inches, 1 millimeters, 2 millimeters. For each measurement, you find the corresponding, let's say for 10 Newton, you find the corresponding stretch. 20 Newtons, you find the corresponding stretch. Next one, 30 Newtons, you find how much the spring is stretched. If you can compress the spring, the other way, the force, the amount of force would be negative because in the opposite direction. It's a vector, remember. If you can compress it, you can measure how much is compressed. How much more, like increasing the force, you'll see it's compressed more. Now what happens is if you connect these dots, hopefully I put them in the right, there you go. This line shows the relationship between Fs, the force in the spring, and how much the spring is stretched. Now, how are they related? We know there is a proportion, there is a relationship between them. This means that if you have a spring like this, right, of Fs, and let's say this is, let me be clear about that. Let's say the spring was here at the beginning. So this is initial length, and now it's at here. So this is the final length, and the amount is stretched is S. So force of a spring is equal to Ks. S being, say, elongation or compression, which is equal to S is equal to L minus L naught. Right? In this case, it's compression, so S is positive. If it's, elongation. If it's compression, L is going to be negative. Right? K, well, F is the force in the spring, and K is something new. It's called spring constant, or a stiffness, or a spring stiffness. Can someone tell me what is the unit for K? If the unit for spring force is Newton and unit for the S, right, the amount of stretch or compression or elongation is meter, what would be the unit for K? So K is Fs over S. Fs being Newton force, S being amount of stretch. What would be the unit for K?
Doesn't it have no unit?
Well, so if F is Newton and S is meter, so F over S would be whatever the unit that gives you the unit for spring constant, which is Newton over meter. Right? So stiffness K has the unit of force, whatever unit is for force, we were talking about units, whatever unit for compression or elongation, Newton per meter or pound per foot or pound per inch, whatever you want to look at it. And keep in mind that comes from the fact that K is equal to Fs over S. F being, let's say, Newton, the unit, S being meter. If you go with the Newton as unit for force and go with inch as unit for length, you will get Newton per inch. So the unit of force, whatever it is in your system of measurements, over the unit of length, whatever it is for in your system of measurements. I'll put it this way. So force, whatever the unit for force, over length. And the next thing you have to remember about the spring, very, very important, is always measured from, let's put it this way, S, always measured from unloaded position, which is L naught. Right? Whatever is the initial length of this, L naught, whatever is the final length, subtract them, that gives you S. Very tricky that you might get lost there. It's very important. S is not what is the length of the spring at any given moment. S is the difference between the length of the spring at any given moment minus the length of the spring at the beginning when it's not loaded. Remember that.
On the diagram that you drew, is L naught supposed to be on the left or the right? It's on the left, right?
So this diagram is for S, right? Meaning that when S is 0, meaning that L and L naught are equal when it's unloaded. Right? When it's unloaded, the final length and initial length is the same. Now, if I apply force, L is increasing. So I'm on the right side of this diagram. S is increasing. Does that make sense?
Okay, yeah. I was just saying because on the right it's also labeled L naught. I don't know if it's supposed to be.
Wait, what happened on the right?
It's they're both labeled L naught. Is it supposed to be like that?
I didn't really label the graph L naught. Oh, you're talking about the spring on the left side?
Yeah,
Oh,
yeah.
yes, you're right. You are right.
Okay, sorry.
I was looking at, sorry, I was totally in the wrong place. I was looking at the graph on the right side. Yes, this should be L. Good catch. Thank you. Should be L, final length. You're totally right. The last type of force is cables and pulleys that we're going to see in this course. Right? So cables and pulleys, and we're mainly talking about cables here, but they come with pack in most cases. So if you have a pulley like this, rotating, and let's say you have, if I can set this up quickly, and let's say you have, bear with me, yeah, there you go. No. Let's say you have something like this. It's a pulley. I have a cable, it's a thread in this case. One side there's a weight, and the other side I'm just pulling it. Right? So the cable is passing through the pulley. Pulley is somewhere fixed, let's say hinged to some fixed place, ceiling, let's say, and I'm lifting this weight. I'm just pulling the thread from one side, and the weight goes. If I stay like this, and at any given moment in a static equilibrium, meaning that nothing is moving, the force throughout this cable, or thread in this case, is constant. So no matter where you look across this cable, on the left side of the pulley, on the right side of the pulley, closer to weight, wherever you want, look at this cable, the force inside this cable throughout the cable is the same. So when we are dealing with cables in this course, we make a couple of assumptions. One is that the force throughout the pulley is the same. So a cable or a pulley, or sorry, a cable or a thread or a rope, you can just replace cable with any of those, is subjected to a constant tension T, we usually represent the force in a cable with a T, throughout its length. So as I said, let's say we have something like this there, right? And we fix it to some ceiling. We have the pulley and the rope is passing through. Can be a weight attached to that side, can be pulling something from somewhere, a box. Whatever force is there is the same throughout the cable. No matter wherever you cut, the force is constant throughout the cable, throughout the rope. Second thing you need to know is that we always ignore the weight of the cable unless we are explicitly told that we have to take that into account. So they have negligible weight pulleys and cables. We don't really take into account the weight. Third assumption, cables, pulleys, ropes, chains, all of these are the same from our perspective in this course. Cannot be, if I can take this out of this, cannot be compressed. So here is a cable, right? Thread. I can only pull it. I cannot compress it. If I want to compress it, it's not like a spring that you can compress it. If I compress it, it doesn't really, there is no resistance. So cables can only handle tension force, meaning pulling. If they go under compression, well, nothing, as if they don't exist in the system. We can totally ignore a cable or a chain or a rope under compression because they don't handle compression force. So they can't, they can only stretch. No, sorry, this is the next one. They can only support tension, or as we call it, we remember when we were introducing the concept of force, pulling. We said force is like pulling or pushing. They only can handle only pulling. Spring can handle both pulling and pushing depending on the kind of spring that we're dealing with. But in this course, pretty much all the springs can handle pulling and pushing. Cable, threads, or chain can only handle tension or pulling. Last assumption that we make about all the cables, pulleys, chains, threads in this course, ropes, is that they can't stretch. What does that mean? It means if I have it under tension like this, pulling, doesn't matter how much more I pull, it does not stretch. It can either handle the force or it breaks. We don't care about breaking in this course. So there is no point or no situation in which our cable changes its length. They cannot stretch. They can't stretch. That's it. That's all you need to know about cables. So 4 forces. Every time I put something in front of you and ask you to tell me what are the forces applied to this system, think about these 4. Is there a weight? Where is it? It always should be downward. Is there a smooth contact between that object and something else? Is there a contact between 2 objects? Wherever there's a contact, there must be a normal force or force because of the contact. Third, spring. Is there a spring? If there is, there should be a force because of that. As long as the spring is under stretched or compressed. If it's neither stretched nor compressed and nothing is applied to it, well, S is 0, so there is no force. Last one, cables and pulleys. Whenever we deal with cables and pulleys, you have to remember these assumptions. Right? The force is the same throughout the cable, wherever you look at that cable. They don't stretch, they can handle compression, and we ignore the weight. Now,